Hi everyone, my name is Karel Devriendt. I'm a PhD student at the University of Oxford and the Alan Turing Institute, where I'm being supervised by Renaud Lambiot. I'm very happy today to present to you my work on the variance and covariance of distributions on graphs, which was done also in collaboration with Samuel, who is at the Polytechnic University in Madrid. So our project started from this network, which is a network of mathematical knowledge, as we say it. And what does that mean? So the nodes in this network represent mathematical concepts such as Pythagoras theorem, right triangles, or Euclidean geometry. And then links between these nodes exist if there's some mathematical or conceptual relation between them. So of course, this network is not readily available, but there are some data sets that give you, based on Wikipedia pages and links between them, that give you a proxy for this network. And so we used the network that was so the data from this paper. Then on top of this network, so we all know that this mathematical knowledge is something that's being used, right, either by researchers in mathematics or by practitioners like data scientists or engineers. And so to study how this mathematical knowledge is being used, we looked at different papers. And so for each paper, we can go and count how often a certain concept is appearing. And then you get things like this, right? Paper A will have this type of concept used, while paper B will have a whole different range of concepts being used. And so we think of these as distributions on the graph. And so the question we had at this point is, how do you measure the difference between these two things? How do you quantify this difference between two distributions? Where for the red paper, you see they're sort of more coherent than for the blue one, which is more spread out on the network. Okay, and so this is a question we were wondering, not specifically for this mathematical knowledge network, but more generally in the case of network science, you often have this structural information and then functional data on top of that. Right, and you'd like to look at those two data types at the same time. So what we did to measure this coherence was to look at the variance of the distributions. And so the variance on graphs wasn't defined yet, but we proposed this new formula where the major novelty we introduced or we took into account was taking into account distances between nodes of the graph. Right, and so distances on a graph is something that some of you might be familiar with, but it's not too hard to imagine that the distance between nodes to nodes can be, for instance, how many steps you need to take at least to go from one node to the other. But there's also other things like the effective resistance distance. Okay, so we propose this formula, and then a few sanity checks like these two examples here showed you that indeed, if the probability distribution is very spread out, like the left figure, then you will get a high variance, whereas in the right figure, if you have sort of a coherent distribution, you will get a low variance. And this all seemed to work out pretty fine. So then we went ahead and did the experiments on our network of knowledge by using over 140,000 archive papers over different fields. We calculated what the typical variances look like. So for instance, for the field of analysis of PDEs, a lot of variances lie in this range between 0 and 10. But then if you look at a different field like combinatorics, you find that also papers exist with the variance that are higher than 10. And so this is a clear qualitative difference, and we don't know at this point where it's coming from, but it shows you how this new tool of variance of distribution on network can lead you to some interesting differences, right? Because these are sort of two modes in which a network is being used. And the variance is here a tool to quantify how different they are. The second type of analysis we did is to compare concepts that appear together in a paper with randomized papers, so as a null model. Right? So what we did is we compared the variance between those, and we found that on average, the variance of the concepts that appear together in a paper will be smaller than if you just take a bunch of random concepts. Okay, and so that seems to confirm a certain hypothesis that indeed the concepts that are being used in a paper are somehow coherent in this network of knowledge, so coherent in the sense that they have relations between them. Second sort of type of results we had were more theoretical. And I don't have the time to go in depth, but I definitely can recommend you to go look at the paper later. But what we looked at is to think of the question, out of all possible distributions, which distribution gives you the largest variance? And if you think a bit through, you'll find that this distribution will somehow put all probability mass on the boundary or the periphery of the network. And so thinking back the other way around, you can actually use this maximum variance distribution to define a boundary in a graph, because in general, that's something that's not really known. Right here, for instance, in the karate club, we found that this can be seen, these nodes can be seen as a boundary of the network. Okay, so that was my very quick presentation about our results. I hope you enjoyed, and if there's any questions, I'll be glad to answer them. Thank you.